Let me just make sure. Okay, you guys are good to go.
Okay. Well, hello, everybody. I'm Bob McNally, and shortly you'll be hearing from Oscar Castellino. And we are your entertainment for the virtual banquet tonight. And before we start, I want to give a shout out to James Burke and the whole technical team that is managing this multi-streamed event with such great flair and aplomb. And thanks to the whole Mars Society for hanging in all these years and hanging in this year in particular. And I'd also like to give a little shout out to MDRS Crew 24 back in 2004. So with that said, I'm going to start things off with the song that I wrote back in 2005, which is called On to Mars. And I know some of the chapters have used that song as a warm-up song for meetings, and I'm thrilled that people have enjoyed the song. And I have to say, this is not as much a Mars anthem as it is a space shanty. It's really a work song. It's about all the work that we're doing in order to get to Mars, and the anthems come into place when we're on Mars, and also for motivating us to get to Mars. But this is a work song, so as such, there is a chorus, and you can see the words over my shoulder for the chorus, and I would like everyone to sing along on this. Now, people might say it's really silly to ask people to sing along on a virtual banquet, but people also might say it's silly to go to Mars. So if you can't sing along on a virtual banquet, how in the world do you expect to get to Mars? So the only limitation I would invite is that the other people who are on the panel do not sing along out loud and mute their microphones, because all our separate delays preclude us from singing simultaneously, much as I would treasure the opportunity to sing with Oscar. So with that all said, here we go. Not getting any computer audio here. What's going on? Bear with. All right, there's always something. Be right there. Here we go. $100,000 ago, we traveled north to dark and cold from Africa across the plains, struggling on that long walk. We learned to make and improvise with sticks and stones. We stayed alive. Our genes are calling down the line, calling to us to move on. We're moving on to Mars. We're headed on to Mars. We're going on to Mars, on to Mars. We're moving on to Mars. We're seeking life on Mars. We're bringing life to Mars, on to Mars. So you've heard it. I expect that next time. Big calypso raft, a skin canoe, a wooden boat out in a storm. Across the oceans we have roamed, immigrants on that long ride. Another ocean there to cross. Mars is waiting there for us. Mars is ready down the line, ready for us to move on. We're moving on to Mars. We're headed on to Mars. We're going on to Mars, on to Mars. We're moving on to Mars. We're seeking life on Mars. We're bringing life to Mars, on to Mars. We've done this many times before, found the skill, made the will, built the vessels sleek and strong to carry us on that next ride. But could it be that we've become too timid to attempt our dreams? Our genes are calling down the line, calling to us to move on. We're moving on to Mars. We're headed on to Mars. We're going on to Mars. On to Mars. We're moving on to Mars. We're seeking life on Mars. We're bringing life to Mars. On to Mars. And now it's time for us to go. We're leaving on that midnight ship in smoke and rumble, flame and roar. Strap in for that high ride. Our courage leads us here to gauge with all who've gone before. Children waiting down the line, waiting while we move on. Our courage leads us here to find Martian home for humankind. Our children's children down the line, thanking us for moving on. We're moving on to Mars. We're headed on to Mars. We're going on to Mars. On to Mars. We're moving on to Mars. We're seeking life on Mars. We're bringing life to Mars. On to Mars. On to Mars. On to Mars. Join that. On to Mars. On to Mars. We're moving on to Mars. We're seeking life on Mars. We're bringing life to Mars. We're going on to Mars. On to Mars.
Wow.
Well sung. Well sung. Thank you.
Great.
And now, please, may I introduce Oscar Castellino.
Hello, everyone. So I'm here on Mars, actually. You can see it's very red. But anyway, this is London, and it's actually 2:30 a.m. So I have neighbors sleeping on either side. And when Robert asked me to perform, I was very happy. But I've got another plan B, which is equally good. So the first thing I'll do is I'll play for you. In 2017, Robert, myself, and James Welland collaborated together and created Rise to Mars, Mars Anthem. So I'll play that for you first. It has the lyrics as subtitles, so you can sing along just like you did with Bob. So here we go.
And next, we have the world premiere of the Mars Anthem with baritone soloist Oscar Castellino, performed by the Repco Symphonia with Andrew Thompson with the baton.
Rise to Mars, men and women, dare to dream, dare to strive, build a home for our children, make this desert come alive. There are challenges before our eyes that nature never knew, but the power of human enterprise shall take us through and through. Rise to Mars, men and women, dare to dream, dare to strive, build a home for our children, make this desert come alive. all together, hopeful spirits, bring an end to strife, for a future lies beyond the skies. Rise to Mars, men and women, dare to dream, dare to strive, build a home for our children, make this desert come alive. Come along, all together, for a future, rise to Mars!
And that
So that was the first performance. I want to ask you, what are you drinking or eating? I got with me a cup of chai because I was born in Mumbai, and we run on it. It's very important. I studied physics in Mumbai, and then I went to study opera in London. And Mars was always very inspiring to me, and I got in touch with Robert Zubrin in 2017, and that's what happened. Exciting. What happened after that was we had a great performance in Wales, where every year they have a huge performance of kids singing at St. David's Hall, and they selected the anthem. So I got to teach children all over Wales to sing the anthem. They came together, and when I entered onto the stage, it was great because there were 1,500 children, and I could speak to them about Mars, and then we all sang. I'll play a short clip for you from that. So yeah, that was an incredible feeling to have all these children singing. We've had a few translations of the anthem. So as many of you may know, the Welsh is sort of the language of anthems, and Wales is the land of singers. And we had a tenor sing the anthem in Welsh, and that was at another quite a big performance with an orchestra. I'll show you some of that. So that was in Welsh. It's a beautiful language to sing, and just like Italian. Right, and we were planning to have it sung in Spanish this year at the European Mars Conference, and Miguel Guerrilla, he had translated it into Spanish. Many of you may know him from the Spanish Mars Society, but we'll do it at some point. And yeah, so I told you that I've come up with a plan B for tonight, and so the past week I've gone and recorded the Mars anthem in a cappella, okay, a new arrangement with what I call the Mars Underground a cappella chorus. So you're going to listen to it now. Boom chaka ba 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 dee ba, boom boom chaka boom. Boom boom chaka ba 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 dee ba, boom boom chaka boom. Boom boom chaka ba 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 dee ba, boom boom chaka boom. Boom boom chaka ba 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 dee ba, boom boom chaka boom.
Rise to Mars, men and women, dare to dream, dare to strive. Build a home for our children, make this desert come alive. There are challenges before our eyes that nature never knew, but the power of human enterprise shall take all together, hopeful spirits. Come along, raging nations, all together, hopeful spirits. Bring an end to strife, for our future lies beyond the skies. Rise to Mars, men and women, dare to dream, dare to strive. Build a home for our children, make the desert alive. Come along, all together, for our future. Rise to Mars.
Thank you. So that was done over the past week, and I will prepare it properly to be uploaded on YouTube. So that was done pretty quickly, and it was a fun experience to do it with in a cappella. Right. So for the highlight now of this section, over the lockdown, I was in London, as I am now during the lockdown, and I was speaking to, and at the start of the lockdown, I was speaking to Linda Shanson, who's an artist in London, and she said, and I said, this is a good rehearsal for, when we travel to Mars, because quarantined and all that in a sort of in a house, like a spaceship. So 3 months into it, she asked me, so how far are we on our way to Mars? And I said, we are halfway to Mars. And she said, that's a good name for a song. So I thought, that's a great, yeah, I should do it. So I wrote to Robert, I contacted Robert Zubrin and mentioned it to him. And in the conversation, he told me about how the people working at Boca Chica are so inspired, and I've been following them on YouTube, for example, and I thought I mentioned them in the song, so they dedicated to people working hard for us to get to Mars, because as we can give the will, and they give us the way. So yeah, so that was that, and I know that Perseverance is almost halfway to Mars, so this is a good time to present this new song, Halfway to Mars.
Innovation, expedition, this is what we breathe. On a mission, past ignition, meteoric speed. Sailing through the distant ether like a shooting star. Breaking limits, lifting spirits, this is who we are. Living a life among the stars and finding what life is all about. Spreading the wonders of the earth far out. We are halfway to Mars. We are halfway to Mars. We are halfway to Mars and going on. Good intense every skill, past the highest hill. We are halfway to Mars and going on. Boca Chica's new outbreak now, all of earthly kind. Indiana to India with a goal in mind. On a quest to give the best to generations on. Breaking limits, lifting spirits, this is why we're born. Living a life among the stars and finding what life is all about. Spreading the wonders of the earth far out.
So that was Halfway to Mars. And I know many of you must be listening from different Mars societies around the world, and I would love to collaborate with anyone who wants to do a translation of Mars Anthem. We have it in Welsh and Spanish, and I think Polish as well. But I would love to do one in Hindi, so if anybody's listening from India and knows of a lyricist or a volunteer lyricist who wants to collaborate on some new music, new translations of and new arrangements of Mars music, please get in touch. And you can just Google my name. I think on my website you can contact me. So that's it from me. And if Robert, I don't know if Robert's here, but yeah, that's it from me. I think we have some time left, but James, over to you.
Yeah, Robert is here. Robert.
Yes, I'm here. Yes, I'm here.
Hi, Robert.
Hi, Robert.
Hi. Okay. Well, I think. Okay. I got on a little late this evening because I was scoring the scores. Has Bob McNally sung yet?
Yeah, he did. Yes.
He did. Okay. Well then, where are we? Well then, the next speaker is Carter Emmert. Is Carter online?
Can you hear
Okay,
me?
and let me
Yes.
just introduce Carter just for a minute. Carter Emmert is actually one of the original members of the Mars Underground, going all the way back to 1981. And he was a kid then, but he is an artist, was an artist, and he became the artist for the Mars Underground. He came up with their famous symbol of the Da Vinci Man and the Mars symbol, and many other things, and many famous illustrations of Mars missions have been done by him over the years. And now he is the artist in residence at the Rose Planetarium in New York, what used to be called the Hayden Planetarium, part of the American Museum of Natural History. And he's prepared a great Mars multimedia show. So take it away, Carter.
Well, it's a great pleasure to be with you all, and I have a video I want to share, and so I'm going to cut to that in just a second. And so Bob, you know, this is the first time I'm joining you all at the Mars Society, so it's a great honor to be with you all tonight. And I really enjoyed seeing you and Elon talk engineering turkey last night. That was great. So without further ado, let me try to share my screen here in just a second. Let me get this going. And let me see if I can share with you all. And James is probably listening in. I have some music with us, which will come for later. So let me share.
Yeah, I'm right here, Carter.
My window. Thank you. I'm just trying to share the right screen. Oh no. Okay. Show all windows. Okay. 2D windows. Just a moment. Let me stop trying to share. Let me see. Okay. My apologies. Okay, now that's playing. And let me pause it. Come back Zoom. Where am I? Here. Okay. Very sorry about this. Hold on. Doesn't want to share my image. Huh. Just say screen one. And hopefully now I can
Yeah, we see OBS now.
Okay.
Okay, now we see your screen. Now we see your video.
Oh, excellent. Okay, great. These are some of my artworks that were done with the original Case for Mars design scenario. Later, after 6 Case for Mars meetings, I went out to work for Carol Stoker on a book project, a compendium of sort of review papers of what came of the Case for Mars. And so that book is called Strategies for Mars, A Guide to Human Exploration. And the color illustrations here were specific for the Case for Mars 2. The pencil drawings were done as sort of thematic chapter openers for the various topics that were in Strategies for Mars. This painting here adorned the cover of Bob's second book, I believe. And the Mars flag was designed by Tom Paine and was sent to us. Here's Buzz Aldrin and I holding the flag at Tom Paine's funeral in 1992. And the design scenario I built into a model for the Smithsonian. It's still hanging on the wall there on the mall in Beyond Planet Earth. These designs here were initial designs from NASA that came along later, ideas for the greenhouse, shirt sleeve environment, inflatable greenhouse. There's Buzz when he was 51 and Leonard David looking younger with more hair. And this was something from the Strategic Defense Initiative and ideas for a plane here. That Strategic Defense Initiative idea for a lander later became Pathfinder, ideas for cheaper missions to Mars. I sort of stopped my artwork and hung that up for going off to the Hayden Planetarium to build what you're about to see. That letter was from Tom Paine that came with the flag. So, so what would be the planetarium of the 21st century? The Museum of Natural History asked that question and built the Rose Center. And in it, the rebuilt Hayden Planetarium, within it is like a flight simulator. And so as we built it, there was interest about it. This is me and Martha Stewart. I was flying her off to the Orion Nebula and flew over the rings of Saturn. This is inside the Rose Center and the planetarium. We're inside the capsule of Apollo 11, actually, as our stand-in for Apollo 8. My friend Maria pointing out Cape Cod, where I'm broadcasting to you tonight. Here we are flying over the Middle East. Leyland Melvin, astronaut, was the head of NASA education. He saw what we were doing. He said, that's the closest I've been to being in space since I was in space. I said, well, that's the greatest compliment we could ever have. This is open space, and this was a tool that we have built over a collaboration going on close to, well, 18 years now with Linköping University in Sweden. And in this tool, which is an interactive exploratory tool that's free to the world, it's openspaceproject.com if you're interested in downloading the software. But here I am basically mixing and matching all these different data sets, which you're about to see. And so OpenSpace is this tool that you can use. And so we're trying to promote this worldwide. We can also link up planetariums all around the world to view this. Mars being a particular interest of mine, I feel that in some ways that I left NASA, I left Boulder to come to New York to try to build an engine that we could really put together all these different data sets, especially in a planetarium, like a giant flight simulator, to take you to Mars. I'll probably never get to go there myself, but with the data that's been sent back by our robots, we have a tremendous ability to really look at this up close and personal. We're coming into Noctis Labyrinthus here, flying in over the hills there are very beautiful. What we're looking at, thanks to Jay Dixon at Murray Labs at Caltech, he's created a seamless, blended, not a controlled image, which means exactly where everything would be relative to the height map here, but it's very good. This is a 5-meter data set gathered by the Mars Reconnaissance Orbiter, which is approaching 70,000 orbits around Mars since it got there over 10 years ago. And these images are then mapped onto height maps, which are gathered. In this case, we have a map, thanks to the US Geological Survey, blending both the Mars orbiting laser altimeter from MRO along with the HS high resolution stereo camera on board Mars Express, HRSC data set. So that gives us resolutions that are on the order. We have a 5-meter resolution here for these images, but at best, we get about 50 meters per pixel for the elevation from the high resolution stereo camera. So we're putting these things together, and then with open space, you're able to fly this interactively. When we do this in the dome, it really is very immersive. If you come to the Hayden Planetarium, we have special programs where you'd be able to see that. But if you do know me, I have a carpet I roll out in the middle for friends, and we take the magic carpet ride. Sometimes we're in the dome upwards to, we've been in there for 4 hours at times. But we do try to also bring that to the public at large with our programming. We're flying in over Western Candor Chasma right now. We're coming down on this 5-meter data set. But inherent to this idea of trying to maximize what we could do with the data sets is really try to put this together at multiple resolutions. And James, I'm not sure if you have the music, but if you did bring it up, what we do in the dome, what I like to do in the dome is use music together with these visuals, flying slow, because if you fly too fast, sometimes the graphics can't keep up. Open space is designed by developers using really gaming technology and graphics cards of the finest generation. And currently at the Hayden Planetarium, even though it's closed because of the pandemic, just last year we installed laser projectors, which are sort of the best in the world, which really pops this image. The atmospheric model in open space is physics-based, so we're dialing in the right parameters and so forth to mix that in and blend this to give you a proper sky. And the lighting is baked in by the satellite when it flew over, sort of 3 p.m. lighting. We're coming up on crenellated, folded, layered terrain of Seti Mensa at the floor of the Western Candor Chasma portion of Valles Marineris. The height of these mountains is extraordinary. What's amazing, we're coming in now to high-rise imagery that gets us down to a 1/4 meter resolution. And so that we can see now hills that are, a couple 100 meters high. So think of sort of a tall building, in an average city, whereas the background mountains are running upwards to about 20,000 feet. At the deepest part of the Euphrates Canyon, it's deeper than the height of Mount Everest. And so we're seeing this extraordinary scale. There's no vertical exaggeration here. This is all one-to-one. And you don't need vertical exaggeration if you have this amount of detail. So high-rise lets us get down close. And also where you have stereo imaging, what that allows you to do is actually put together, extrapolate the height. This is extraordinary. This cliff wall in Euphrates Canyon, the central mountain section, and that was targeted by the high-rise team because they had seen it was fresh. This is northeast Melis Chasma, and these beautiful scree slopes that come down over these cliffs. And I'm flying along this and sort of pivoting around. Now, this stereo imaging of high-rise allows us to get down to about 1 meter resolution in elevation. We're flying over another high-rise terrain here, in the southern portion of Euphrates, and so that we see the sand dunes, and they're absolutely gorgeous. Mars becomes landscape with this, and that's in the grand tradition of the American Museum of Natural History, where we celebrate the flora and fauna of Earth, but also the geology of Earth, the geography, these spectacular sites of Earth, that Mars really becomes alive with these data sets. And so the goal here was to really take us to Mars and make that as palpable as possible. Coming up on Olympus Mons right now, it would be hard to go to Mars without visiting the volcano. So we're coming into the caldera. I'd like to say that for Bob's sake, this is larger than Brooklyn. It's in fact larger than New York City. It's about 50 miles wide, so it's huge, a couple thousand feet for the height of the cliff face that's around it, of course. So, we just move on and on and on in this. It's a tremendous wealth of data and information. For as large as Olympus Mons is, there are small volcanoes in the base of the Euphrates Canyon. We're now flying over Mojave crater. As NASA likes to say, if we're looking for water, if we're looking for life, follow the water. Well, what could have carved this? Either rain after this, this is probably the youngest crater, Mojave. It's about 30 miles wide. This is, we're over the eastern flank, we're now over the western flank, over high-rise terrain. And we see basically a lot of fluvial action here. Perhaps it snowed, and then sort of, then we had this fluvial erosion, perhaps it was rain. But also this process of taking stereo, we also take CPX 5-meter data. And my high school students from the Bergen County Academies in Hackensack, New Jersey, they're highly achieving students. It's one of the highest placing high schools in the New York tri-state area. Very smart kids, and they're able to run the NASA AIM stereo pipeline to actually derive height fields for us for a lot of this. And so part of that is what we saw when we were flying over Western Candor before we added in the high rise. So here we are, we're coming in sort of helicopter move. I like to sort of dive bomb this terrain. I'm kind of pushing my computer to the limit here, maybe stuttering a little bit. But it's really extraordinary where technology can take us now. For those of us who may not make it to Mars because we're too old, that perhaps this is an inspiration for that next generation. I wanted to bring us here to an extraordinary set of features. This is in Ganges, Tasma, one of the part of the group of canyons that make up Valles Marineris. And these are these white sulfate mounds, and there are 3 of them. They're not quite as tall as the Tetons, but sort of think of the Tetons in this sort of class. And then we have these darker olivine-rich sand dunes that have blown around them. And so we'll continue along here. There's some beautiful alluvial fans that come off of this particular set of mounds. And I remember seeing pictures of this early on, one of the first high-rise targets before they had stereo. So that, I mean, but I had this sort of wish to sort of go there. What would it be like if we could just, you know, really see that? Well, open space has made that possible. And so we hope that you'll download it. Speaking of the software, just a little bit, it's developed in collaboration. Well, it's NASA funded. I should mention that first and foremost. Thanks to the Science Mission Directorate, Science Activation Group, which we're part of. And we were funded in 2015 after NASA sort of caught wind of the visualizations that we were doing for the Pluto encounter. And so from that, we basically proposed from this collaboration that we were doing with Sweden, with Sweden's Linköping University. And so working together with the talents there in their media technologies group, my friend, Professor Anders Innerman, we started working together in 2002, led up to this open space software. And so in collaboration with us academically are the University of Utah and also the, this may loop again, because I think the video is actually over. Maybe if I just share screen to one thing, I had difficulty tonight actually getting the video together. So I'm just going to come back into, if I could stop screen sharing here, I have that control, but I may just try to screen share my OBS so that I might be able to at least just give you some credits here, which are all important to put up. So let's see, I may just go to, well, okay, this is sort of compromised because you're seeing you're seeing some interface here on top of the graphics. But maybe if I widen this out, it might be a little better for you. I couldn't help but just show you coming into Ebbswalde Delta, just north of Holden Crater. And again, this is another high-rise terrain and emphasizes the places that we want to go. I was going to put some of Jezero Crater in here, but I got sort of carried away with the various places that I wanted to include, and then I had some difficulty just getting it together at the last minute. I thought about flying live, but I thought it'd be easier to sort of spotlight in discussion these things as we go. So I was mentioning that Open Space is this academic collaboration between the American Museum of Natural History, Linköping University in Sweden, and University of Utah's Scientific Computing and Imaging Institute, as well as New York University's Tandon School of Engineering, supported by NASA, freely available. And if you do go to openspace.com and download this and start to use it, we have tutorial videos. We have a list of all our papers. It's open source, it's on GitHub. And also we have an active Slack channel. So if you need help, let me go to just the next movie. Right here, let's see, if I can click on something else so we don't see that red thing. We're coming in over Curiosity. This is another project of our thesis students from Linköping. They were master's students that have really built the code for open space. So we're coming in to basically, we have skinned the point clouds that are generated in stereo from the rover. And here we see telemetry readback, basically, from Curiosity doing its operations. So that we have that full history that we can read and then go from there. So let's see, well, we'll pull out, I guess one of the last things I want to say is I was a kid, I was 8 years old when we landed on the moon. This is Neil Armstrong. This is a photogrammetry I did of LEM 2 in the Smithsonian, but then we put it on the LROC terrain models of the Apollo 11 landing site. And I witnessed this when I was 8 years old. And for the young members of the Mars Society, I hope that you get to Mars in my lifetime so I can see this again, landing on a new world. And with that, I just want to sort of bring up some thanks. And let's see, I'll close off all these other things so we can see the thanks to NASA, our open space partners. And if you were hearing any music, I'm not sure if James got that in, but I had something prepared from the Mermen and the Supertones, two of my favorite surf bands, and just to remind us that we come from a water planet. Thank you very much.
Hi, Carter, do you want to take a few questions?
Sure, and I'll stop sharing. There we go.
Okay, are there questions for Carter Emmert?
I can't hear too well.
I'm not sure if we have the webmaster has stepped away. Oh, there's a few in the Q&A.
Hi, this is Carrie. Hey, can you hear
I
me?
can hear you. Yes, great.
Right. Robert, can you hear me? This is Carrie.
Yes, please. So why don't you read off some of the questions that are coming in?
Thanks, Carrie.
Sure, absolutely. The first one I have is, it says, someone would like to know. Did you hear me?
No, it suddenly cut out just when you were going to mention the question. So sorry.
Oh, okay, I'm so sorry. Let me try one more time.
I hear you now. Yeah.
Okay, great. Robert is asking, not Robert Zubrin, but Robert Slater is asking if they can see the new logo.
See the new logo for for open space?
I'm sorry. That's what. Yeah. I'll ask you another one.
Okay.
Yeah. Why don't we let me ask some of them?
Thanks,
Go
God.
ahead. I'm not sure why you can't hear me.
Okay. What's Atash Gallagher asks, what system is this simulation running on? I certainly hope you guys get the new cards and processors to let it run on its full potential.
Yes, actually, and thanks for asking that. It's multiple operating systems. It's been developed in Windows, so it sort of perhaps runs best in that. But we're running on the latest NVIDIA cards, but it also we have a Mac version, and you can compile for yourself on a Linux version.
Okay. Another Holger Eisenberg from Germany is asking, says, great work. How is the individual frame registration done that they join well together to a seamless surface? Do you plan
Thank
to
you.
move to an...
Yes, we're using the Geospatial Data Abstraction language, or GDAL, and that's open. Since we're open source, that everything has to be open. And so the Open Geospatial Consortium has constructed GDAL that allows us, if we have, geospatial data from various sources. I mentioned in my thank you also to Lucian Plesa, originally from Romania, who spent 20 years at NASA JPL, and he's now at Esri. And he works a lot with Trent Hare at the USGS for planetary maps. And Lucien guided us in using GDAL. So that we built open space in particular to, for planets, for globe browsing. It could be Earth, could be the moon, as you saw at the end there. And you saw some of Earth just up there in the pictures of the dome. But it allows us to take various data sets and layer them in. And also, if we have regional areas of interest, like the high rise, that we can, we have formatting that we can do, so we can layer it in both elevation and imagery. Yes. Mm-hmm.
David Zhao asks, how accurate is open space to the real thing?
Well, we're not doing any height exaggeration. I would say it's extremely close. It's about as close as you can get. I mean, everything that we're doing is a data visualization system. I mentioned, I started to go down the rabbit hole to say that this global map of Mars that Jay Dixon has done at Murray Lab, it's not controlled. And control means that you have a very precise set of reference points, and that everything has to fit precisely together and to be on this sort of global network of exact points. They did that for Themis, and Themis has a 100-meter resolution. CTX has 5-meter resolution, so it would be a monumental task to register all that exactly so, and register it to the height map and so forth. Sort of our best reference we have is the Mars Orbiting Laser Altimeter, because it had to be referenced not to the surface, which is the way mapping had to occur. It's sort of a control net of points based on mosaicing pictures together. But with the laser altimeter, we had to basically be referenced to the barycenter of Mars. And so with that, MOLA provided this sort of basic reference grid for everything else. And so what I like to say is that when you fly over features in open space, sometimes you'll see that the height map and the image are just slightly off, but really just slightly off. Trent Hare from USGS likes to say, don't try to land a rover on these images. And I'm like, that's not my worry. I'm not engineering rovers and where they're landing. What we're doing is trying to bring the rest of the world in as accurate as we can make it as possible. And really, I love doing artwork, but I sort of hung up my pencil and my paintbrush to manage programmers and be sort of intermediary between the scientists and basically the engineers to allow us to then bring this to the world as a major institution of the United States. And but also we have tremendous collaborators all around the world. As I mentioned, Sweden enabled this. So that's a great honor to work with all these people.
I've got a question for you, Carter.
Yeah.
One of the things that really impressed me most about your artwork, the drawings you did and so forth, was the humanistic aspect of them, of showing people in these situations and so forth. And you showed some of them earlier in your talk. Now you're working in a new genre. Do you see any potential for bringing humanism into this genre?
Yes, because what we have is the sort of tabula rasa of Mars. So if you wanted to build a base, so here I'm talking to the Mars Society. I mean, it's like if you have models that you'd like to place, I mean, you can take open space and you can do that. But also, this is sort of the closest we can get without, just sort of going there yourself. I mean, soon we'll have people back on the moon, and hopefully that we might be able to combine this sense of virtual reality attempts essentially with the people who are really there. We have a model of the International Space Station and discussion with a group that did one of the European astronauts took pictures and did photogrammetry inside the ISS. And so you would have this image-based model that I'm very much looking forward to seeing, on the dome of the planetarium. People ask me what oh, can this do virtual reality? Yes, we can do stereo. There's stereo settings for it. But I like to say my headset has 400 seats in it, which is our theater at the Hayden Planetarium. But I think this notion of what I was, I talked a lot through this whole thing. But what I like to do, and I mentioned these multiple hour sessions of people laying on the floor and looking up as we fly over, over Mars. I mean, you're really, I mean, we can do this over the Earth too. Some of you may know that if you're friends of mine on Facebook during the pandemic, early parts of the pandemic, I think I did 80 shows. We were doing this every night, flying over Earth and diving in, flying over mountain ranges and things like this. And people would get frustrated because we had music and I wasn't talking. And they'd say, where are we? And they want to know. And I kind of like that, because when you back away, we are a planet. There are no borders. The borders are in our heads. Mars is a place without borders. So, you know, I play with naming mountains. I was going to point out, especially with Alan coming up, a mountain which I like to call, it's in Nacus Labyrinthus, but I call it Mount Planet Pluto. And next to it, there's another mountain right next to it. So I call that Clyde's Peak. So, you know, and there's also Mount Charon, which is smaller over to the side. You know, you can't help but sort of look at all this and realize that this is built on a mountain of people. My first science conference, I flew out to Caltech in high school. I turned 18 at the second Mars colloquium. And that's where I met Chris McKay and Penny Boston and Carol Stoker. Tom Meyer has passed on, and Steve Welch, and together reformed the case for Mars. Chris McKay called me in the summer of 1981 and said, get off your butt and form a student group out here so that we can hold the conference, because they needed sort of a token undergraduate to basically host the meeting or pull that
Carter,
together.
we have about 3
really,
minutes.
the grad students pulled that together. But this human aspect of this, at that science meeting, I met Clyde Tombaugh. I actually dined with him on my 18th birthday. I didn't know who he was. And when he told me, I just about fell off the chair. And I also met another fellow who, on another night of that meeting, where he and I sat across the table from one another, and that was Tim Mutch, 6 months before he died. And he was the head of the Viking mission. And these things are personal. None of us live forever, but this is an intergenerational thing. And Mars is that spear into the future where humans can go. And it'll test our ingenuity. And you all in the Mars Society, this is personal. This is about us. It's about humanity and taking life off the planet. That's huge.
All right. Just one quick question. Michelle from Montreal asks, can this come to other planetariums like ours in Montreal?
Absolutely. In fact, I'm good friends with some of the people there in Montreal. Yes, in fact, this digital technology is getting cheaper, easier to use, and so on. So we've done this. This also, Mars is just part of the whole universe. This was really built to visualize what we call our digital universe atlas. And that goes all the way out to the cosmic microwave background. And so all the galaxy catalogs, all of that, look us up. Mars is of particular interest. And so especially to you all, I just wanted to share with you that Mars is closer than you think, because you know this stuff has come back to us from space, and that the more that we take that and put that together is pretty extraordinary. I think, you know, being on Mars would be a tough thing to do. Some of you are tough enough, you're going to do it, and we'll figure things out and how to live there. But for now, maybe the closest we can get is to appreciate what that looks like. But it also is kind of a mirror back to us from the water planet, that this water planet is very special. It will always be home. And a lot of people, when I take them to Mars, after a while, they say, can we go back to Earth? They want to come back to the cool green hills of Earth.
Okay, well, we're going to bring some green hills to Mars.
Good.
All right. Well, thank you, Carter.
Well,
Lee,
thank you, Bob. Thanks for inviting me.
Okay, this is great. Lee, can you turn on my video here?
Yes.
I want to thank James Burke too, because he really helped me out.
Okay. Is
Alan.
And there's Alan Stern, and presumably I'm live somewhere here.
Astronaut Alan Stern.
Okay, that's future astronaut. Well, okay, he's been a high flyer for a while. Okay, listen, this has been great. This shows both Carter's presentation and Oscar and Bob, the power of art. Okay, power of art, you know, allowing us to feel and see things that have yet to be felt and seen. Okay, so, and, you know, this is important. But now I'm going to introduce Alan Stern. You know, came out of my interview yesterday with Elon. Between the two of us, we worked out what is now the slogan of the Mars Society, which is where there's a will, there's a way. And and no person better proves that than Alan Stern. Okay, I first met Alan Stern, I guess, in the early 90s, and he had this crackpot idea that we should send a probe to Pluto because, you know, we'd gotten to Neptune and, you know, you got to get all 9. And and he fought for this, basically single-handedly convinced the space community to do it. And then he did it, led a team that accomplished this. So he is now the man who has gone further than any man has gone before. And so what better way to bring this conference to a climax than to hear from the man who did that. So give Alan Stern the floor.
Well, thank you, Bob. That was a wonderful introduction, and thank you for inviting me here this evening. It's a privilege to come and talk to the Mars Society and share the story of this farthest exploration of worlds. And I have to say, Carter just gave a fantastic presentation. I was listening to the whole thing as I listened to many of the plenaries this morning. And Carter, great job. I think I'm going to share my screen now. And
You are sharing.
okay, you ought to be able to see PowerPoint. Carrie, maybe you can let me know when you see it.
We see it now, and you sound great.
Okay, thanks on both. Okay.
You're welcome.
So I'm going to give you a whirlwind tour of the story of New Horizons and some of the things that we discovered along the way. And let me thank Bob for the kudos about being able to get the United States and humankind to Pluto. But I have to say, it's a team, all space flight is a team sport. In the end, 2,500 men and women worked on New Horizons, primarily during the development phase. And every one of them deserves credit for making this happen. Just as many, many thousands, if not tens of thousands of people will get credit when we send humans to Mars for being a part of that project. All right, let's dive in. And I had a little trouble advancing slides. There's the first slide. This is a pair of pictures of myself in front of the New Horizons launch vehicle and inside the nose cone of that rocket with New Horizons above me on the right, very early in 2006, just days before we launched. And I show this pair of images to say, for those of you who don't know me well, I've had the great privilege of working on very many space missions in my career. I've been on the science teams now of 30 missions, from suborbital to orbital to space shuttle missions to interplanetary missions. And I've had the great privilege of being PI of one type or another on 14 missions. And New Horizons is absolutely my favorite, without a doubt. And how could it not be? I think for all of us who worked on this project, to be a part of a first mission to a new planet is something that planetary scientists and the engineers and technicians and others that put these missions together is something that we all crave. It was the gold standard in the 60s and 70s and even the 80s to be a part of those early first missions, first to Mars and Venus with the Mariners, and then on to Mercury and Jupiter and across the solar system with Pioneer and Voyager, all the way to Neptune. And for all of us who worked on this, I have to say, we often say to ourselves, It sounds like science fiction, but it's not. We built a spacecraft that journeyed all the way across our solar system to explore the farthest worlds ever explored in the history of humankind. And that's probably a record that won't be topped for a number of decades. I hope to live to see not just humans on Mars, but also robots back to the Kuiper belt, even an orbiter of Pluto, and the exploration of other worlds in the Kuiper belt. But that's the subject of another talk. In any case, this has really been an epic journey of many billions of miles and now many years since we began. I'm only going to be able to talk about some of the very top level details of this project and what we learned. But with David Grinspoon, I wrote a book called Chasing New Horizons that's available everywhere. And if you want to read more about it, that's probably the best way to do it. 220 pages of goodness that tells much of the story that I can't even go into tonight. But you might wonder, and a good place to start is, how did we get to do something like this? How did we get to lead this project and carry it out? And I have to say, it was a long road, as Bob was alluding to. It actually started in the summer of 1989 when Voyager was finishing its last exploration at Neptune, when a group of young scientists, very much like the Mars Underground of the early 80s, a group of young scientists in the late 80s dubbed themselves the Pluto Underground and began lobbying NASA to build and fly a spacecraft to Pluto. If we'd had any idea how long it would take to succeed at that, we might not have started. Because as you see in this graphic, there were quite a number of instantiations of attempts to get a spacecraft off the drawing board and into construction to fly to Pluto, or even two spacecraft in some cases. And it took us all of the 1990s and a whole series of cancellations and into the early 2000s before New Horizons was born, which is the only one of this series, of course, that ever got off the drawing board. But I worked on every one of those, as did many other people in the scientific community, the engineering community, and at NASA headquarters. And it really was a difficult slog. Every time we thought we were close, something would happen. Either something in the political winds would happen, something in the budgetary winds would happen, or a change in fashion in the way NASA does missions. Or at one point, we were very close to getting a new start, and Mars Observer blew up just days from reaching Mars. And the NASA administrator of the time decided to take the money that would have gone to start a mission to Pluto and begin the Mars program that we know and love today. In any case, it was a long haul. And I'm showing now, I'm sure this looks very pixelated and blurry. This is the very best image of Pluto ever made before New Horizons. It's not much. I was PI of this program with the Hubble Space Telescope in the mid-1990s. At that time, we knew that Pluto was going to be a fascinating object. We knew that it had an atmosphere, that it had a giant moon, probably formed the same way that the Earth-Moon system is formed. We knew that Pluto had interesting surface markings, and these images, this one and others like it by the Hubble, back in the mid-90s, just after the Hubble repair, allowed us to actually see it for the first time as anything other than a point of light. But still, you can't do much with an image like this. You really don't have the resolution to learn very much about your target, and that's why we go to these places, is to put our cameras and spectrometers and other sensors up close and personal, where we can really write the textbook about these worlds. Now, how did we get this mission from the interesting A-list to the very top of the A-list so that it could receive funding in such a competitive environment as the NASA planetary program? Well, what really made the difference is the story of scientific discovery that I want to tell you now in the next couple of slides. When I went to school, when I was a grade school student and learned a little bit about our solar system, and probably when most of you did, you learn that the solar system's architecture consisted of 4 rocky planets on the inside, down close to the sun and surrounded by an asteroid belt. And then beyond that, on much larger orbits, are 4 gargantuan gas and ice giant planets. And beyond that, there was this odd footnote called Pluto, discovered in 1930, that didn't fit either the pattern of the terrestrial planets or the giant planets, and which was a real head scratcher. And from the time that Clyde Tombaugh discovered Pluto in 1930, all the way until that Voyager encounter in 1989, and even a few years beyond that, this was our understanding of the architecture of our solar system. But it was completely wrong. We thought the solar system had 2 zones, the terrestrial planet zone, the giant planet zone. But beginning in the early 1990s, telescopes here on Earth began to discover Pluto's cohort, another population, really the 3rd zone of our solar system, called the Kuiper Belt. This is a view looking down on the solar system of actually discovered Kuiper Belt objects, where the dots out beyond that outermost circle, which is the orbit of Neptune, the dots represent those individual objects at their actual locations. And you'll notice among them, there's some larger ones. The larger dots represent larger objects, Pluto being the one down here, if you can see my cursor, at roughly the 6 o'clock position. I'll say more about that in just a moment. But this discovery of the Kuiper Belt that began in 1992 with just 1 discovery, and then the next year with 4, and the following year there were 10, and now there are thousands of objects that paint out the Kuiper Belt's architecture that have shown us there is a 3rd zone to our solar system. It is the Kuiper Belt. And it is, this is a 3-dimensional view, if you will. It's a side view of that same distribution of large and small objects. And from the ones that we have discovered, and an estimate of how much of the surface area of the Kuiper Belt we have surveyed, we know that we've only scratched the surface. We've only discovered the tip of the iceberg. Of the thousands of objects that we have discovered, it is predicted that there are actually hundreds of thousands. And we have also discovered that not only is this the largest structure in the planetary system and the 3rd zone of our solar system, but it is teeming with dwarf planets. Pluto is not a misfit. It was simply the first and the brightest of these discoveries, the easiest to discover. But there they are. There's Eris and Makemake and Haumea and Sedna and Quoar and many more in this new 3rd class of planets, which we call the dwarf planets. They're just smaller planets, just like the sun is a dwarf star. And it was this discovery of the Kuiper Belt and its implications for the origin of our solar system and the realization that there's a 3rd class of planet in our solar system that we had never been to, despite decades of planetary exploration, that led the very first planetary decadal survey in 2003 to catapult the priority to fly a mission to Pluto and on beyond Pluto, deeper into the Kuiper Belt to study small Kuiper Belt objects, to the very top of the funding queue. And Congress listened, and the administration listened, and the result is the funding that made New Horizons possible. But actually, New Horizons was selected not because of that decadal survey, but a couple of years before, hoping that the decadal survey would make this decision. NASA put out an announcement of opportunity. A series of teams formed, including our own, and competed to win this mission to Pluto and the Kuiper Belt. And we each wrote big, thick proposals, roughly 1,000 pages of engineering, cost, and management. Those were judged against one another. And fortunately, our proposal, this is the cover of the New Horizons proposal back in 2001. Fortunately, our proposal was selected. That was in late November of 2001 when I got a phone call from NASA headquarters saying that New Horizons was the selected team. And the result was that all of us who had promised to go and build this spacecraft and get it launched ended up in a kind of a whirlwind 4-year project to do what took Voyager and most other planetary missions 6 to 8 to in some cases 10 years to do, which is to design and build and test and get a spacecraft to the launch pad. We only had 4 years and 2 months to do this. And to top it off, to make it harder, we only had 20% of the budget, 2 dimes on the dollar of what it took to do Voyager. So we had to invent a whole new way to do this. We had to break the price mold. We had to break the schedule mold. And those 2,500 men and women that worked on New Horizons really rose to the challenge. It was 52 weeks a year and 7 days a week for those entire 4 years and 2 months. And I could tell you stories, but we don't have time about the commitment that it took. But I will remain in awe the rest of my life of the people who worked behind the scenes to get this together and to bring it to the launch pad. This is a cartoon view of the New Horizons spacecraft. For reference, that dish antenna, the high gain antenna, is about a little over 2 meters in diameter. That sets a scale for you. You can see the names of the 7 scientific instruments on board. There are color and panchromatic imagers, medium and high resolution telescopes, ultraviolet and infrared spectrometers, radio science, plasma spectrometers, and a student-built dust counter, the first ever student-built instrument to fly on a spacecraft. And that is something I'm very proud of, because now it's become the norm in planetary science to include those kind of payloads built by students at universities and operated by students at universities on very many planetary missions. This is a picture of New Horizons down in Florida shortly before we put it on the rocket. This picture is a great one in my view, because not only can you see the spacecraft without all of the multi-layer insulation on it, so you can see the superstructure, you can see some of the scientific instruments like this one and that one. You can see the radioisotope thermoelectric nuclear generator that powers our spacecraft, just like Voyager, Cassini, Galileo, the pioneers that also traveled too far from the sun to use sunlight. And there are people there for scale that show you this spacecraft is barely the size of a baby grand piano, yet it contains not just the 7 scientific instruments, but all of those flight systems and redundant copies of those inside that box to make this entire journey across our solar system. The other thing that you may not realize, but looking at this image, there's only one spacecraft there. You know, when Pioneer 10 and 11 were launched to be the first to Jupiter, it was still in the days when we had the luxury of being able to fly 2. Same for Voyagers 1 and 2, but in the case of New Horizons, we just didn't have the money to do it. So we had to build in enough reliability to do it with only 1 try. And we rose to that challenge. And even today, nearly 15 years after launch, New Horizons is operating flawlessly, and so are all 7 of its scientific instruments. So one of my favorite pictures of New Horizons, on the day that we fueled the radioisotope thermoelectric generator, Friday the 13th of January, 2006. That's myself standing in front of the spacecraft, which is inside the nose cone of our Atlas V launch vehicle, inside its hangar at this point. And that's the day that we really began the mission. Even though we didn't launch it, that's the day that New Horizons became electrically live, and we began operating it from our Mission Control Center in Columbia, Maryland, at the Johns Hopkins Applied Physics Laboratory. And it wasn't very long, just 6 days later, that we launched that spacecraft on that enormous Atlas V, which gave us a flawless ride to Earth orbit. And 40 minutes later, used the Centaur upper stage to take us out of Earth orbit onto an interplanetary trajectory, and then lit a custom-built Star 48 solid rocket motor that was inside the nose cone beneath New Horizons to boost our orbital speed and energy to take us out to Jupiter for a gravity assist that would speed us on the way to Pluto. And the combination of that enormous launch vehicle, that solid rocket motor for a fourth burn, and the Jupiter gravity assist is what allowed us to cross the solar system in record speed in only 9.5 years. Let me give you a feeling for how fast New Horizons left the Earth. At the end of the burn of that solid rocket motor, from that time until we reached the orbit of the moon, was not the 3 days of Apollo, roughly 90 hours, but only 9 hours. We launched at 2 in the afternoon on Thursday, the 19th of January, and by 11 p.m. that night, Eastern time, the spacecraft had crossed the orbit of the moon, about 10 times faster than Apollo missions took to reach the orbit of the moon. And we're still traveling at that high speed, boosted, of course, by Jupiter's great gravity. Here's our route of flight. The launch, as I said, in January of 06, Jupiter flyby just 13 months later. Compare that to Galileo, 6.5 years to reach Jupiter. Compare that to any of the more recent Jupiter missions. Cassini went to Jupiter and took 4 years to do it. We did it in 13 months, and then on across the great gulf of the middle solar system, the orbits of the giant planets, on an 8-year journey that basically spanned the two Obama administrations until we reached the Pluto system in July of 2015. And there's Pluto's orbit in yellow, and you see that our trajectory, the red line with an arrow at the end, crossed Pluto's orbit just as Pluto was crossing the plane of the solar system. On our way, as I said, we did a Jupiter gravity assist, and this was the only object that we flew by along the way. These are images from that flyby, from the cover of Science magazine, what I call Rolling Stone for nerds. This is Jupiter and its volcanic moon Io in color, as seen by New Horizons. We had a tremendous scientific flyby of Jupiter in January and February and early parts of March 2007. But moreover, that flyby, besides being scientifically rich and our gravity assist to take us to Pluto, was also the flight test of most of the software that we used at Pluto for target tracking, image motion compensation, all of that we needed, and we needed to work. So this flyby served all three of those purposes, and it just worked out flawlessly. And then we flew on for those 8 years, which I will skip here, and take you right to the flyby of Pluto in 2015. Here, the larger image on your left is at the Johns Hopkins Applied Physics Lab, just outside of our mission control. That's Glenn Fountain, who was our long-term project manager for New Horizons. And in the inset in the upper right, you see our mission control with one of our flight controllers there. And then one thing I want to point out about this flyby is, although all of the great data that we collected was all of the really high resolution images, the high resolution composition spectra, the atmospheric data, everything else that you see in textbooks and everywhere else on the web, for example, everything that I'll show you was collected in just a couple of days around the closest approach, which was on Bastille Day, the 14th of July. The actual flyby was a 2-year-long flight operation that began 6 months out with optical navigation imaging, with course corrections to hone our course to Pluto, and then was followed after the intensive data collection with 16 months of data downlink back to the Deep Space Network antennas on the Earth to get all the data that we collected back to Earth. And to give you a scale, the amount of data that we collected at Pluto was about 100 times as much as a Voyager flyby tape recorder load. So a tremendous amount of data by first flyby standards. And I also wanted to show you the geometry of the flyby. The Pluto system is like Uranus, tipped over on its side, and it was basically pulled on to the direction of our flight. And so we pierced the system with times there shown in hours on the morning of the 14th of July, essentially perpendicular to the orbits of Pluto's 5 moons, Charon being the large moon, and then the 4 small moons that orbit outside of Charon. We had very difficult navigation challenges to meet in order to fly through the shadows of Pluto and Charon and watch the sun set and rise and the Earth set and rise for the occultation experiments. But our navigators and our flight control team carried that off perfectly. In fact, after a 9.5-year journey, New Horizons was only 86 seconds off course. And I'm very proud to say we were 86 seconds early. This is an image of our main target, Pluto, in the lower right, with its large moon Charon next up to its upper left, and then 2 of the 4 small moons. That's Hydra and Nix in this family portrait made by New Horizons. This is in true color. But most of the pictures you see now, like this one, are in enhanced color, where we've, in the computer, driven the color up to the rails. We've stretched the color or the target so that you can see the contrast between redder and bluer or yellower areas on the planet or on its satellites. This is the binary pair, Pluto and Charon. For reference scale, Pluto is about 3/4 of the distance from the United States west coast to east coast. And Charon, which is not to scale in this image, it's bigger than its actual scale, so that you can see more detail, is about the size of the state of Texas. And of course, when you look at Pluto, you can immediately see that it's very different from Charon. It's brighter, it's more colorful, it's got a greater degree of surface geology variation. It's got that giant heart on the surface, which I'll talk more about. That's a giant nitrogen glacier, which we have since named Sputnik Planitia. Sputnik for the first satellite. In fact, one of the naming themes on Pluto, which I nominated, and really our whole team nominated, but I asked for, was that in completing the reconnaissance of the classical planets known at the birth of the space age, I wanted a naming theme to honor pioneers of space exploration, pioneering missions, pioneering teams, and pioneering individuals. And so Sputnik, the largest feature that we see on the flyby hemisphere, is named for the very first and most pioneering robotic mission ever, the Soviet Union's Sputnik, first satellite in Earth orbit. Here's a close-up view of Pluto images in a mosaic that we wrapped on a sphere as if we were flying above Pluto ourselves. This is the view you would get if you had the eyes that New Horizons had flying along that trajectory. And you can see mountain ranges and a little bit more detail down on the glacier. You can see giant fissures emanating from Sputnik. These are tectonic faults, if you will, caused by the giant impact that created the basin in which, the impact basin in which Sputnik lies. And I just wanted to show you this behind the scenes picture if you haven't seen it before. It was taken by a New York photographer named Michael Soluri, who I invited to join our team shortly before launch. And he chronicled our team and its activities from before launch really to this day today, even out in the extended mission. And this is, I just love this shot because it's candid. It's really at the very moment that some members of our science team were seeing the first high resolution picture of Pluto in our science analysis room at Johns Hopkins on the morning of the flyby, a couple of hours before this image was released in a press conference that we did that morning. And you can just see the emotion in the room. And I love it because for all of us who work so long and so hard to get a mission to Pluto, and then to compete for a mission to Pluto, and then build it at breakneck pace, and then fly it across the entire solar system with only one shot at getting this right, I just can't tell you how much this meant to all of us. But you can see how excited those people are. There are many images like this, and many images of high fives and hugs and so forth at this flyby and at our subsequent flyby in the Kuiper belt. And some of those will be published next year in a book by the University of Arizona, but I only have time to show you this one. Here's Pluto in true color. You can see the geologic complexity across the surface. You can't see its atmosphere, but it's there. It's made mostly of nitrogen. It's at pressures and temperatures that are very similar to the Earth's upper atmosphere and the mesosphere. There's that giant heart, the glacier Sputnik Planitia, and also dark regions called maculae. Here are two of them. This one's called Cthulhu, informally, and there are 5 more, and we've given names to all of them. Some of them are on the far side. Here you can see more of the tectonic features, including a great rift valley stretching north and south, probably also associated with this impact basin. But I'm going to show you close-ups and give you a feel for the stunning geology on Pluto's surface. So before I do that, I should say that Jeff Moore at NASA Ames, our planetary geologist who leads our planetary geology team, has called Pluto the new Mars. And I thought it was particularly appropriate to mention that here for all of you at this Mars conference. I won't have time to point out the many similarities between these 2 different red planets. But as I walk through the next half dozen or so slides showing you some details of Pluto's geology, many of you will recognize that from glaciers to heavily cratered terrains to young terrains to some of the activity features that I'll show you on the surface, they all have analogs on Mars, virtually every one of them. So let's take that tour. And I want to start with this beautiful view of snow-capped mountains on Pluto. I live in Colorado, and of course we have snow-capped mountains. These mountains way out in the Kuiper Belt are not snow-capped with water ice. That bright ice at the top of those mountains, which by the way, are about as high as the Continental Divide here in the United States. And this scene, since it doesn't have a scale bar, is about the size of Western Colorado. But those bright snowcaps are actually made of condensed methane. That's CH4, or the natural gas that's used in heaters and some kitchens here on the Earth. But at Pluto's temperatures, it's a solid, and it condenses out and plates out on the tops of very tall mountain ranges on Pluto. Here's another individual place on Pluto, and if you're wondering where each of these places are, there's a context image, and the little green box within the bigger green box shows you where on Pluto we are. This is just showing you very heavily cratered terrain, and because it's very heavily cratered, we can be sure that this is a very old terrain, which we have age dated through techniques of crater retention age to about 4 billion years old, about as old as the planet itself from the birth of our solar system. Very old terrains, and right next to it, out on the glacier, we see young terrains where there are no craters at all, which we can't age date because we don't see any craters to date it with, but we can set an upper limit age of only 10 million years. In fact, those individual ovoid and semicircular cells that you see are convection cells in which the nitrogen ice is overturning due to a thermal gradient in the glacier, a vertical thermal gradient. And that erases craters as they're formed. And the best models we have indicate that those individual cells turn over about once every million years, maybe even every 500,000 years. And so that's probably the real age of this surface that we're seeing, which is 10,000 times younger than the these places on Pluto that are very old. We also see evidence of enormous avalanches where snow falls or runs down valley chutes out of these mountain ranges, again, 4 to 5 kilometers above the glacier, which is here on the left, and pool out on the plain, in this case, pool about 50 miles across or a little bit larger. So enormous avalanches of material. And here again, you see no craters, so this avalanche was in the geologically recent past. But if that's not enough, we find cryovolcanoes and other sorts of volcanic constructs on the surface at a number of different places. This particular cryovolcano is about the size of Mauna Loa on the Earth, about the same diameter and about the same height above the surrounding terrains. It is enormous, and you'll notice there are no craters on its flanks, so it is also young, created in the geologically recent past. It's named Wright Mons after the Wright brothers, pioneers in aviation. And here's another type of terrain. Who ordered that terrain in an area several hundred kilometers across off the eastern side of Sputnik in Tambov Regio, which we call bladed terrain. Each of these blades that you see that are aligned are made of methane ice, and they are probably condensates out of the atmosphere. They run for hundreds of kilometers. How they are organized to be aligned like this, we think has something to do with sublimation processes and the action of the faint sunlight warming the terrains, even if feebly. But in addition, each of these blades is about 1 kilometer high. So if you were standing on the surface, you would see them stretching up thousands of feet in your sky, and to your left and to your right, stretching over the horizon. And in fact, as I said, hundreds of kilometers. This is a type of terrain that's very prevalent, not only here on Pluto, but also on Pluto's far side, and which has no analog anywhere else in the solar system, a completely unique type of terrain. We even see evidence for at least one paleo lake, this one about 25 kilometers long with a distinct shoreline, and we know from stereo imaging that it sits in a hanging valley in mountains to the west of Sputnik Glacier. And we know from compositional mapping that that lake, at least the surface of it, is made of condensed nitrogen. But you can't have liquids on Pluto's surface today. The temperature and pressure just don't allow it. The temperature and pressure are below the triple point of nitrogen where liquids can exist. So we think this is forensic evidence that attests to a previous era in which Pluto had a much thicker atmosphere, much like Mars had a thicker atmosphere in its ancient past, and much more abundant liquids on its surface. Pluto apparently had both running and standing liquids, but not water, nitrogen in this case. Just an absolutely geologic wonderland, a world with complexity far beyond its size gives it any right to have, and which, because of its current day activity, from avalanches and cryovolcanoes to this vast overturning glacier, Sputnik, which is about 1 million square kilometers, larger than the state of Texas on the Earth, and yet is active today, indicates that somehow Pluto's geologic engine, unlike the Earth's moon and many other small worlds in the solar system, Pluto's engine has not run out. And how it is powered today, 4.5 billion years after formation, how it powers such vigorous geology after all this time is a mystery that still hasn't been solved. And I think it'll take an orbiter to go back to really learn how that geology is powered. And now let me close on Pluto with this set of images from the highest resolution strip from the North Pole down onto the glacier, in which we can fly over Pluto's surface as if we were in a very high-speed airplane and travel more than 1,000 miles from the North Polar regions caked in snows of nitrogen, over heavily cratered terrains in which you can see layering beneath the surface, to dust devil tracks in the snow, onto badlands, and then very large water ice mountain blocks covered in a veneer of nitrogen and methane. And then onto the shoreline of Sputnik Glacier, in which you see dune fields, convection cells, and other phenomena, including wind streaks, that just attest to the range of geology that you see across Pluto. What a spectacular world we found at the other end of the solar system. And then we went on. As we were charged to do by the Decadal Survey, New Horizons was built to go on with the power and the communications capability and the warranty, if you will, the design for life, to go on deeper into the Kuiper Belt, to fly by at least one small Kuiper Belt object, these so-called planetesimals that are the building blocks of the planets. And the value in this is not just pure exploration, that's one value, but the real scientific value is that this region of the solar system, being so far from the sun, is both cold and undisturbed. And that Kuiper Belt object that we flew by, named Arrokoth, which means sky in the Powhatan Indian language of Maryland, is the most pristine object ever explored by any spacecraft, 4.5 billion miles from the sun, and kept in this deep freeze near absolute zero for all these billions of years as a kind of archaeological dig, if you will, into the history of the building block, the history of formation of the building blocks of our solar system. That flyby, as it says, took place on the 1st of January, 2019. Arrokoth was discovered by us after a 4-year-long search for a flyby target within our fuel reach. We actually found Arrokoth along with several other candidates to fly by with the Hubble Space Telescope, and traveled another 3.5 years and more than 1 billion miles to reach it in early 2019. There's a depiction of our path across the Kuiper belt after Pluto. But I want to give you a feel for just how difficult this task was. Beyond finding this little needle in the haystack, let me run this very short 8-second video. It's going to zoom up on Pluto onto Sputnik Glacier and then place Arrokoth for scale. Have a look at this. Down on the glacier, and boom, there's Arrokoth. This little target, no larger than the scale of a county here in the United States, which has a reflectivity that's so dark that it's almost draped in velvet and only lit by the sun at 44 astronomical units, so several thousand times fainter sunlight than we see here on Earth on a bright sunny day. All conspired to make the navigation challenge to hunt this little guy down and in a one-shot get it right or go home flyby at almost 35,000 miles an hour. New Horizons succeeded again and brilliantly. And I chalk that up to the team of professionals, the flight controllers and engineers, and the science team that runs it, and all of those folks that help build it and get it launched. It's just an amazing piece of American workmanship. And I'll show another video. This is a set of images made in the fall of 2018 as we were flying up to Arrokoth against the star fields of Sagittarius, where the spacecraft is headed. And you'll see Arrokoth pop out of the star field as a little faint ember and grow in brightness and move through the parallax caused by the motion of the spacecraft primarily over a period of several weeks. This is how we hunted it down. So Arrokoth, there it is, right in the center, moving to the bottom. And we can play that, I think, one more time. There we go. Here comes Arrokoth. There we go. Okay, now we'll move on. Well, like that picture of the candid picture of the team at the moment the first high-res image of Pluto appeared, this is a picture in our geology and geophysics room at our mission control at 2:30 in the morning on the 1st of January 2019, when the first high-resolution image of Arrokoth appeared. And again, you can see the team's emotional energy there. And what a weird and wonderful Kuiper belt object this turned out to be. It's really taught us such a great deal. Meet Arrokoth. Here are high-resolution images of it. I just have a few to show you. It is a contact binary. The two lobes were initially distinct objects that somehow gently came together. This is a clue to how these individual lobes formed. I'll say a little bit more about that. You see a complex geology on the surface. For scale, from stem to stern, this object is about 20 miles long, 33 kilometers to be more precise. And it's very highly flattened, which you can see in this set of tweened images made by a Russian amateur image analyst named Norman Tkachenko to illustrate from New Horizons data just how flattened these two lobes are. That's another clue to the way that Arrokoth and its two lobes individually formed. And here it is in color with a little geological map as an inset to just tell you that we have all kinds of data. They're all on the ground now. from this flyby. It took a long time because the bit rates are even slower from this greater distance. So it took longer than getting the data back from Pluto, even though we took just about as much data. The bit rates were lower. And from that, we learned a great deal. I skipped ahead. I want to say what Arikov has primarily taught us is about the composition of the distant nebula out there where the Kuiper belt was formed, and about the mode of accretion of these building blocks that threw away the standard theory of planetesimal accretion in favor of a much newer theory that's only been around not 50 years like the standard theory, but only about 15 years, that indicates that all of these objects were gently assembled in little local particle cloud collapse accretion mode called pebble cloud collapse, which now has become, for all intents and purposes, as a result of New Horizons, the standard theory of planetesimal formation, at least in the Kuiper belt, but probably also down in the inner solar system where planets like Mars were formed from similarly small objects that very likely were formed by this pebble cloud collapse mechanism. I'm going to end with just a few more slides, and this is the last image from New Horizons I'll show. It's my favorite image of the entire mission. It's a true color image of Pluto, made looking back on the morning of the flyby as we flew through Pluto's shadow, and its atmosphere, which is truly blue, was backlit by the sun. And the reason I love this image so much is not for its scientific value. There is scientific value. For example, if you look closely, you can count the structure in the haze layers above Pluto's limb. But more importantly, the only way to get an image like this is to get it from the far side of Pluto. And for all of us that worked so long to see a mission funded, then built, and then flown all the way across the solar system, this was the culminating image. That's why it's my favorite. It's kind of the equivalent of the Apollo Earthrise image in terms of accomplishment. And for all of you that are working to get humans to Mars, this took us a long time. From the time that we first started a conversation to go to NASA and ask for a study of how we would possibly send a spacecraft to Pluto in 1989, until we got all the data back in 2016, it was 27 years. I know you've been working on getting humans to Mars for longer than that, but these long hauls pay off, and so does persistence. And so I want to encourage you to keep at it, because I think we're closer than we've ever been to getting humans to Mars. And I think we'll see it in our lifetimes. I also want to show you a couple of other images. This one is from our mission control. You can see the clock in the back. It's just 4 seconds to Pluto flyby closest approach back there in the summer of 2015. And I just want to say thousands of people came to this flyby because they wanted to be a part of it. People from all walks of life. And I have to say, I think this is just a small taste of what we will see when humans are ready to set foot on Mars. So is this. The fact that we were on the front cover of 450 newspapers all around the world the next morning, that we got the Google Doodle, that we were on countless magazine covers, that we were the biggest web event NASA had ever seen in the flyby of Pluto, with literally 2 billion visits to our website in 48 hours. And I think that the landing of humans on Mars and that first expedition will put this to shame. I think the entire world will watch. The entire world will be wired by the 2030s when we do this. Even those who don't have internet will soon have it, thanks to the LEO constellations that are being launched and that are about to be launched in the 2020s. And when we go to Mars with humans, I think it's going to be one of the most emotionally powerful and moving and inspiring events for STEM education and for many other purposes that we've ever seen. And I'm very proud that the flyby of Pluto could be the biggest event of its time, but I'm sure that it'll be dwarfed by what the first expedition to Mars does. Let me also say to all of you, keep at it. because the other red planet besides Pluto beckons, and it's time to get serious. And I'm so happy to see that Jim Bridenstine this morning made such a call and such an emphasis on going to Mars once we practice at the moon. It's around the corner now. I can feel it, and I hope all of you can feel it. And thank you for letting me talk about the exploration of Pluto and the Kuiper Belt by New Horizons and the New Horizons team. So back over to you, Bob, and if there are any questions, I'd be happy to answer.
Robert, do you want to present questions to Alan?
His microphone is muted. Go ahead, Lee.
Okay, so we do have a few questions for you here, Alan. Thank you. Oh, here we go.
I'm unmuted.
Okay.
Okay, no, I'm here. Okay. To Alan Stern, have we found, or what are the plans to find a second Kuiper Belt object to fly by?
That's a great question. We have not found one yet. We have about an eighth of a tank of gas left, the hydrazine in the spacecraft propellant tank. Coincidentally, that's about as much delta V capabilities it took to do the Aircraft flyby. We just started the searches for flyby targets and other scientific targets in the Kuiper Belt this summer in June, using the giant Japanese Subaru telescope on top of Mauna Kea in Hawaii. This year, as a result of those searches, we found 73 Kuiper Belt objects along our path, many of which we can study with our telescopes and imagers, but none of which are close enough to reach. Now, don't be discouraged, even though we know it's a long shot to find one before we leave the Kuiper Belt. We're going to look under every rock. It took us 4 years to find Arrokoth, and we're not going to quit after one season of looking for the post-Arrokoth target. So stay tuned.
Okay, Jerry Stone from Great Britain writes, my name's on the New Horizons spacecraft, so I designed a bumper sticker. It said, my other vehicle has gone to Pluto. So he says, is Pluto a planet?
Well, you know, just take a look at it. I like to use the Star Trek test. That's the simplest way to determine what's a planet. You know from watching Star Trek that when the starship shows up at a new place and the viewfinder and the bridge comes on, you pretty well know if they're orbiting a planet or an asteroid or a star or an alien spacecraft right away. And but all kidding aside, the geophysical planet definition, which is the definition that most planetary scientists use, calls anything big enough to be rounded by self-gravity. It's not so large that it's doing nuclear fusion like the sun. Anything that's big enough to be rounded, what we call a planet. And Pluto way qualifies for that. It's actually about 10 times the diameter of the smallest objects that qualify. That means we're going to have a lot of planets in the solar system. We better get used to it. We can look up their names in a book. There's no need to memorize them. Pluto is what got us really thinking about what it means to be a planet. It sent the astronomers in a tizzy back in 2006. They still haven't gotten over the fact that there are an astronomical number of planets, but planetary scientists have. And when you go to planetary science meetings, or you look in the planetary science literature, you see everything from Pluto and its kin in the Kuiper Belt to large satellites like the Earth's moon and Titan and Ganymede and Triton and many more called planets. And so by planetary science standards, you better believe Pluto is a planet. And I'm very happy that it's also the real number 9.
Okay. Do the two lobes of Aberoth have a name? Arrokoth have a name?
Arrokoth's lobes do not have a name. And in fact, neither do any of the surface features in the sense of an official name. We have individual names for surface features that we use informally, but we haven't yet submitted names for surface features on Arrokoth. We just refer to the two lobes as the small lobe and the big lobe, and that does just fine.
Ahmad writes, he says, could there be a black hole near the solar system? And let me just amplify that. Could there be other unexpected types of objects near the solar system?
Yeah, well, I don't know enough to know firsthand whether there could be black holes, tiny black holes in interstellar space that are currently within the distance of the Oort cloud and therefore within the solar system or not. I know that there are some scientific papers out there on that, but I'll be honest to say I haven't read any of them, so I can't really judge. But today with Google Scholar, you can go out and judge for yourself. So find those papers and take a look. To answer Bob's question, I'm sure that there are many types of objects that we have not yet discovered, particularly in the Kuiper belt and the Oort cloud. The Oort cloud is what I often call the solar system's attic, because all the objects in the Oort cloud were ejected there during the final stages of clearing of the giant planets. And I'm sure there's a wide range of exotic objects. Most provocatively, there are probably small planets or even mid-sized planets like Mars that were in the game in the inner and middle solar system, formed with all the rest that we see today, but which were ejected out there to this great deep freeze, and which we will someday find. I think that census will be largely complete at the end of this century. But today, we have to only speculate. The great thing about the planetary astronomy ahead is that all those discoveries are going to start with this new generation of telescopes, the extremely large telescopes coming online in the 20s and then the 2030s. And I just can't wait to see what's out there.
Are we sure that all these objects in the Kuiper belt and the Oort cloud were created with our solar system? Could some be from other solar systems?
It's an excellent question. When solar systems form, including our own, computer models show that clearing of giant planet regions ejects objects not just to Oort cloud-like structures on the lip of their gravitational potential well, but also throws many more objects out into interstellar space than get deposited in Oort clouds. And even though our Oort cloud is estimated to have between 100 billion and 1 trillion objects in it, many more objects than that were cast out into interstellar space. And every solar system with distant giant planets should be doing the same thing, or should have done the same thing in the past. So interstellar space should be teeming with all kinds of exotica, asteroids, comets, equivalent of Kuiper belt objects, dwarf planets, large planets, black holes, and brown dwarfs for that matter. And from time to time, the larger objects and the rarer ones come through our solar system. And then the smaller objects, like interstellar comets, come through all the time. We just began discovering those. And so stay tuned on those discoveries too. We're just at the very beginning of this era.
1 minute.
Okay, basically, several questions are basically asking, how far can we go with current technology? Can New Horizons reach the Oort cloud? Could another probe with current technology reach the Oort cloud?
New Horizons, if its health continues, can probably go on to about 100 astronomical units out, which is not yet the Oort cloud. We're going to run out of power on that RTG, which has a half-life and produces less power every year. We're going to run out of power by 2040, maybe even a little before that. But with current technology, it's possible to build missions that go even faster than New Horizons and which operate longer. And so, for example, today there's a mission called the Interstellar Probe, which is on the drawing boards. And if it's highly rated in its decadal survey, it'll get built and launched perhaps a decade from now and wants to travel out to 1,000 astronomical units. And I am also part of a startup company called Helicity Space that's looking at a new technology for fusion drive that could take us out to way beyond 1,000 AU and do it with technology that's essentially ready today in the laboratories. It's much easier than creating fusion power, in fact. And I don't have time to talk about that because I think my time is up. But we do have the technology to explore much farther out than we have, and I hope to live to see that.
Okay. Thanks a lot, Alan. That was great.
Thank you, Bob. It's a pleasure.
Okay. So I need to pull up some stuff here.
Hi, Robert. I'm still working, so if you want to give me just a couple more minutes, I will send it to you.
Okay. Can you, you mean on the trophies?
Yes.
Okay. Well, if you can show the trophies when I, if you could, yeah, well, we'll need you to send them to me.
Right, I just need a few more minutes.
Okay, is Alan still here? Or has
he is not.
he has
Carter
not.
or Oscar might be, but
Okay, hold on a second. Let me see if I can see this. Okay, before okay, I can see some.
I just need a few minutes.
Okay, I have all right. I can do the awards now.
Right, but that's what I'm sending you in just a couple minutes.
Well, I can see the list of the awardees.
Whatever you want to do, Robert. I'm letting you know that I'm not ready yet.
Okay. Well, while Carrie gets ready, I'm just gonna talk a little bit about what's happening. Can people still see me, by the way?
Yes, you're good and you sound good.
Oh, thank you. All right. I don't know if I'm good, but I'm great. All right. Anyway, so look, first of all, we're going to shortly announce, first of all, awards to Mars Society members who've done outstanding performances, outstanding jobs over the past year to make all of our work possible. But the other thing that makes our work possible is money. The conferences like this, the operation of the Mars Desert Research Station, the organization of rover contests, none of this is done for free. I mean, we're not paid. I'm not paid. Other Mars Society volunteers are not paid. But there are still costs, the software to run this conference, which, by the way, is a unique historical event. We hit on the idea of having an international teleconvention and not just a set of videos to show, but a real conference where people could come together from all over the world. And it was implemented, and I think it's the first of its kind done by anyone anywhere. We have, by the way, over 10,000 people have registered for the conference. Over 60,000 people have tuned in to watch the interview I did with Elon Musk. And he's very excited about it. So, you know, we put up a link for people to donate. We made the conference free, but give what you can, you know? I mean, if everybody could give $50, we would be in great shape. And if you can't, you know, you go to a church or somewhere and they pass the hat and you throw in $5 or $10, do that. And if you are well situated with funds and can give $1,000, do that. Do what you can. But what I'm going to do right now is I'm going to start announcing the volunteer awards. So first of all, the first award goes to, can I show my screen on this right now? Hello?
You should have a share screen button down at the bottom if you move your cursor down to the bottom of the screen. It's a green box that says share screen.
Yeah, okay, share. I don't want to see that. Okay, so the first award goes to Attila Metsaros. He's the Assistant Director of the Mars Desert Research Station, and this award is for outstanding service at the Mars Desert Research Station from 2019 to 2020. Okay. Let's see. The next award goes to Lauren Wright for her internship at the Mars Desert Research Station for outstanding service at the Mars Desert Research Station from 2019 through 2020. The next is to Frank Crossman. He's the Chief Archivist and Editor for outstanding service and extraordinary work on the Marspedia and for editing the Mars Colonies book. And by the way, Frank is already hard at work. He is going to be putting together a book of the Mars City-State competition entries, all 20 semifinalists and finalists, the 20 out of the 176 are all going to be in that book. And we hope to publish it hopefully by the end of the year. So by the way, Frank will be, I think he's already been in communication with the teams, but if he hasn't been, he will be very shortly. And teams, want to have your material in the book, just work tight with Frank. Another is for Jim Sikowski for outstanding service and extraordinary work on the Marspedia, working with Frank Crossman. Another to Carrie Fay, who is one of the people who made this conference possible. She is the administrative director of the Mars Society. She put in untold hours. She's working right now for outstanding service and extraordinary work on the Mars 2020 virtual convention, treasure, membership, and everything else she does. So she's one of the people that, you know, this is happening because of her. And let me just say, I want to make sure I got David Mateus, Assistant Director of the Mars Desert Research Station, for outstanding service at the Mars Desert Research Station from 2019 through 2020. All right. Frank Crossman, Jim Kukowski, Carrie Fay, and then, let's see, to Jim Burke, or James Burke, Director of Information Technology for outstanding service and extraordinary work on the 2020 virtual convention. This convention was made possible and made extraordinary by the genius and hard work of Jim Burke. So Jim, I just want to thank you. You are amazing. This conference has been amazing. It's world class. It's been an epic event, and thank you, thank you, thank you. So now, let me see. I want to make sure.
I'm sending it to you right now.
You're sending me something right now, huh? Okay, hold on, everyone, because we're getting ready to announce the winners of the Mars City-State competition. Let's see if it's here somewhere.
It's sending right now.
Okay. The electrons are slow tonight. Okay. I just want to say, while I'm waiting for Carrie's electrons to show up, that this city-state competition has been an extraordinary event. And, you know, 176 teams narrowed it down to 20 semifinalists, all of which were excellent. Okay, and then we had to narrow down from then to the 10 finalists who were top drawer. And now we're going to hear the 5 winners. But beyond that, I just have to say, in listening to these talks, I was inspired. People sometimes ask, what good is all this thinking about Mars going to do for us here on Earth? And what I was hearing was all sorts of ideas for how to organize and how to find a way towards a much better human society. The kind of societies that were being outlined that we could hope to build on Mars. When we begin the world anew, how can we do it? And it's worth thinking about. And, if you didn't see these presentations this afternoon, take the time sometime to go on YouTube and just listen to them, because they're just amazing. And of course, get the book. Okay, so
there's a couple that are missing their team pictures because I didn't receive them, but we can post them later once I do.
Well, I don't have your email has not come yet, Carrie.
Okay.
What is this? Ad block?
It's a slightly large file, so it might just take a moment.
Your ad block has been done. What the hell is this? Do we know where? How do I get rid of this thing?
Can you just exit out that window? Just close that window.
Yeah. Okay. So I have
share your screen.
I have closed that window, and hold on just a moment, if you would. I want to stop sharing my screen while I try to fetch your email.
It's the excitement of live calculation.
Okay. Now, what did you just send me? The images of the trophies, was it?
No, I sent you the presentation for the winners.
Oh, I see.
You should have it by now.
Well, this is going to be hard to do.
You just have to open up the PowerPoint that I just made.
Is it possible, Carrie, that because the problem with this is I don't want to show all the winners before.
You won't. I made a PowerPoint.
Well,
So
okay. I just got your PowerPoint.
Okay, you should be able to just open my PowerPoint. Stop sharing for a moment.
Yeah. Well, I believe I'm not sharing right now. Is that true?
Yes.
Okay.
And so you are live but not sharing. So
Okay.
just
So
don't
let
share
me
it so you have it ready.
All right. Hold on a minute. Now, when I share this, I'm going to be sharing. What's this one? These are prizes. Oh, I see. But it's going to be hard for me to do this without showing the people. I guess I can do this. All right, this way. All right. So now I have, hold on, to share my screen.
There should be.
Wait. That's the fourth.
Well, just close that out and then just put the.
Okay. All right. I got it. So I think.
Okay, but make that big. You should just play the presentation.
Play a presentation? Just hold on a second here.
Okay. It's the slideshow.
And right now, I'm just going to walk through it.
Okay.
And you have it in the correct order, correct?
I do.
All right.
It goes from 5th to 1st.
Correct. All right. Very good. Let me take it from here. Okay.
Robert,
All right. Please.
slideshow. And
Yeah,
I'll
please.
post
Please. Okay. All right. So, we're now going to present the awards. So, first is 5th place. In 5th place, with 1,520 points, 20 judges turned in scores. The maximum score anyone could theoretically get was 2,000 points, but these judges were tough judges. And by the way, you'll see how close this contest was. In fifth place with 1,520 points, we have Team Korolev Crater SAR. So there they are. Congratulations to Team Korolev. So now we're going to send you the money and a trophy, but we can't send, I guess we can send the money over the internet, but we can't send the trophy. You'll get it in the mail. All right, so now fourth place, okay, with 1,523 points, okay, beating Korolev by 3 points, we have Flegla Prime, okay. All right, and I guess we don't have a picture of them, but they're going to get $1,000 in a trophy. In third place, and they will get $2,500 and a larger trophy with 1,546 points from France, Team Navarro. Okay, and truly excellent presentation, I must say. Okay, and now we move on. So that was Team Navarro, Remy, Team Foundation. And here we can see some of the people who were on that team. So this was a French team and they claim third place. For second place, who will receive an award of $5,000 and a truly handsome trophy. Okay, an outstanding team for sure. Southern Cross Innovations from Australia. Okay, in the land down under, the Aussies take second place. And now, finally, coming up, first place, $10,000 prize. Okay, and with 1,583 points. The winner of all of them Nexus Aurora, international team from United States, Netherlands, South Africa, and many other countries. This is an international network. They were really impressive. They actually did experimental work demonstrating the ability to make basalt fibers that they were going to build their colony out of. So congratulations to Team Nexus Aurora and to all the teams. Great job, all of you. So let's see. So now I will stop sharing and just talk. Am I on the screen now?
Yes, you are, Robert.
Okay, so that's the awards, we, that calls to the conclusion of tonight's virtual banquet. I think this has been an extraordinary evening. We've gone as far as anyone has gone. We have seen visions of the future. People are going to create the future, and many of these teams that were winners tonight are going to, I know, are going to continue to work. There are working groups that continue to advance their designs. I don't know what our contest is going to be next year, but we'll think of something. And if you didn't compete this year, or if you didn't win this year, you'll have a chance to, once again, contribute your talent to thinking about how to create the human future on Mars. So just want to say a couple of things. We are about to be faced with an extraordinary opportunity. The political deck is about to be shuffled. That will create an opportunity to introduce new ideas into space policy. If Starship reaches the stratosphere by the end of this year, which I sincerely hope it will, that will be a shot heard around the world. And so we need to be ready. We need to be ready to spread the word. That is what we do. Where there's a will, there's a way. Let's spread the will. Thank you, and we'll see you all tomorrow morning at 9 o'clock Pacific.
Robert, you can go ahead and stop your video. We're going to stop the presentation and the conference for this evening.